and welcome to Calculus Examples. I'm Dr. Finch. Today we're going to look at the limit as x goes to infinity of x sine of x over x cubed plus 1. So when we see something like this, the thing that we should definitely, our eyes should be drawn to will be the sine of x. So notice we've got a trig function that's stuck inside of a polynomial divided by a polynomial. So whenever we see that, there is one theorem that should be sticking out in your head, and that should be the squeeze theorem. So oftentimes the squeeze theorem is going to look something very similar to this, where you have some sort of polynomial divided by a polynomial and either sine of x or cosine of x stuck in there as well. Squeeze theorem takes advantage of the fact that if we have some of our trig functions like sine of x or cosine of x, we are going to have those things are bounded by a positive one and a negative one, right? There is our function sine of x. So that tells us that sine of x lives always between 1 and negative 1, no matter what. We're not going to get bigger or smaller than those two numbers. So when we multiply every part of our inequality by x divided by x cubed plus 1, we can see our inequality holds. It doesn't change at all. So the goal here will be to show that the outer two bits of here, of this inequality, go to the same number, because if these two numbers go to the same number, when we take the limit as x goes to infinity, that means that the number in between, the x sine of x over x cubed plus 1, is going to be squeezed and forced to go to the same thing as well. So to figure this out, we're going to have to figure out the limit of our two outer points on our inequality. So let's start off with the limit as x goes to infinity of x over x cubed plus 1. This should feel somewhat familiar to you. And in this case, because we have a polynomial divided by a polynomial, we're going to look for the largest degree that we have in here, which is the cubed. And we're going to pull that number of x's out of the top and the bottom of our function. All right, so we're going to pull out x cubed, 3x's out of our denominator. That is going to leave us with 1 plus 1 over x cubed. And if you want to, you can multiply it back in to make sure we did it correctly. On our numerator, we're going to pull out an x cubed. And because there was a single x there already, we are going to be left with an x squared. So that is going to cancel out those x cubes. We're going to be left with 1 over x squared in the numerator, and in the denominator, 1 plus 1 over x cubed. Whenever we have something of that sort, keep in mind that our function, this is one of the graphs that you should know. There's very few that you really need to memorize, but this is one of them, is y is equal to 1 over x. Because variations of that, like the one that we see here, 1 over x squared, 1 over x cubed, are going to follow the same pattern, which is as x goes to infinity, that number is going to go to 0. So this gives us a 0 on our numerator and a 1 plus 0 in our denominator. Because our denominator is non-zero, we're good to go. We don't have to worry about, anything funky happening. All right, same exact thing is going to happen with the other side of our inequality. The only difference is we have a negative x on top. We'll go through this one a little bit quicker. We're going to go and do the same method. So we're going to pull out an x cubed on the top and the bottom. And the only difference, again, is that negative is going to keep on following through. So the cubes survive. Negative 0 is still 0. So that tells us that when we have negative x over x cubed plus 1, that is between x sine of x, x cubed plus 1. which is less than or equal to x over x cubed plus 1. Because the outer two bits go to 0, that means the inner part of our inequality must also go to 0. Now, the last thing I would say is make sure that you use the word squeeze theorem somewhere in your proof, the actual words, right? Your teacher is going to expect you to use those actual words there by the squeeze theorem because they like to see that, or at least I did when I was teaching. We are going to have our solution gives us 0 for this particular limit. So this is a wonderful example of the squeeze theorem. I hope you learned something and I hope you enjoyed it. Thank you for listening.